but oh yeah, okay. Hopefully this changes things. Okay, so welcome all. Excited to have 4 talks today. The talks are going to be about 10 minutes each, and with like maybe a couple of minutes for questions. We are excited to have Jane from MIT starting us off about distributional lifting theorems.
Thank you. Hello. Oh, wait, I need the controller. Is there a remote controller for, is it this? Just press play to go to the next slide? Yeah. Okay. Hello, I am Jane. I'm presenting a distributional lifting theorem for pack learning. This is joint work with my wonderful collaborators at Stanford. I'm from MIT. So typically, pack learning research takes place in one of the following two settings. There's distribution-free pack learning, where you make absolutely no assumption on the distribution over the input domain. It's completely arbitrary, and the distribution can be arbitrarily complex. Or you're in the distribution-specific setting, where you assume that the distribution over the input domain is something known, and typically something nice, such as product distributions over the Boolean cube, or the uniform distribution over the Boolean cube. And, you know, learners in the distribution-specific setting are typically much more powerful than learners in the distribution-free setting, and more expressive classes can be learned efficiently. But the downside is that it's limited in practical relevance because it's not very realistic to assume that real-life data is going to be product distributed. So for an example of a large separation between the distribution-free and the distribution-specific setting, we can take the class of intersections of constantly many half spaces over the Boolean cube. There's a cryptographic lower bound for learning even intersections of just 2 half spaces to any non-trivial accuracy. However, over the uniform distribution on the Boolean cube, there's a polytime algorithm for strongly learning any intersection of constantly many half spaces. So we've got a polynomial time algorithm versus a cryptographic lower bound as a separation. So why is this the case? Well, we have algorithmic tools that are very specialized for product distributions. Typically, this is Fourier analysis, and this gives us very powerful algorithms for distribution-specific pack learning. However, in the distribution-free setting, you can embed hard problems, like cryptographic hard problems or NP hard problems, into the distribution to prove lower bounds. And in this case, all the complexity is in the distribution. The function class can be very simple. It just needs to be expressive enough that you have to solve some problem about the distribution in order to output a good predictor. So how can we interpolate between these two extremes, where distribution-specific has this unrealistically optimistic assumption that you might have product distributed input, and distribution-free has this unrealistically pessimistic assumption that the distribution encodes a hard problem? Well, we want the best of both worlds, where we give learners that have complexity that scales with both the complexity of the target function class and the complexity of the distribution. And even better would be to transform a distribution-specific learner into something that works for a more general class of distributions in terms of the complexity of that distribution. Intuitively, we want that if both the target class and the distribution are nice, like have concise representations, then we want to do better than the distribution-free bounds. So here we're looking at a measure of distribution complexity that we're calling decision tree complexity of a distribution. So this depth 3 decision tree represents a distribution over the Boolean cube. The leaves are distributions D1, D2, and D3 that come from a known distribution family F. So think of F as being the class of product distributions or something like that. So when you condition on a path in this tree, so all inputs such that x1 is -1 and x2 is +1, conditioned on this event being the case, the distribution is distributed according to D2. So this is a special case of mixtures of distributions in F that are supported on disjoint subcubes. Our main result is a lifting algorithm that takes an algorithm for learning under the base distribution family F and builds a tree and then outputs a hypothesis, and this learner should work over all distributions that are represented as depth D trees that decompose into leaves that come from F. So the blow up in sample complexity is what you expect. It's, you take the original sample complexity and you multiply it by the number of leaves, which is, in this case, 2 to the D, and the time complexity blows up a little bit more than that. Natural parameter setting is one where the size of the decision tree is polynomial, so the depth is polylog n, So in this case, if you start with a poly-time and sample complexity learning algorithm for the base distribution family, then you end up with a lifted learner that has polynomial sample complexity and quasi-polynomial time complexity. An extra result that we give is a little bit of a generalization. We also can handle distributions that don't decompose into decision trees, but instead decompose into subcube partitions. This is a little bit more general than a decision tree. It doesn't require that the disjoint subcubes have this hierarchical structure of a decision tree. So this work is building on previous work that examines a special case of this problem, where the leaf distribution family contains only the uniform distribution. The algorithm that's discussed in previous work has a much more powerful sample oracle, which is a conditional sample oracle. So you're allowed to draw samples from the distribution conditioned on an input following a specific path. And in addition, its sample complexity is generally higher. It blows up as m to the d rather than m times 2 to the d. And it's also not noise tolerant. So the main changes in this work are that we get rid of the conditional sample oracle and we have just random examples. It handles an arbitrary leaf family. It doesn't have to be uniform. It gains this noise tolerance property, and we also give this generalization for subcube partitions. The difference in the algorithm between previous work and this one is that previous work required that it was a two-phase algorithm where the first phase is to learn the distribution itself as a decision tree. And this decision tree hypothesis had to have very, very small TV distance to the ground truth in order to work. In this work, instead of trying to learn the distribution, we actually don't require that the tree structure match the ground truth of the distribution at all. Instead, we're directly minimizing error of the hypothesis on a test set. So the algorithm's very simple. We just sketch it this way. You draw independent samples, a training set and a test set. You use the training set to run the leaf learner on every possible depth d restriction. So there are n to the d such restrictions. And you've got a leaf hypothesis for each one. Then we're going to build a tree that stitches together these hypotheses, and we're going to output the one that minimizes error on the test set. And so the final form of the hypothesis looks like this. You've got these internal nodes that index a hypothesis. When you receive an input, you follow its path in the tree. You output its classification according to the hypothesis in its leaf. So yeah, it's really that simple. It's really just a decision tree search algorithm. So the analysis is just this. Since you know that D really does have a ground truth decision tree into leaves from the known family F, we know that there exists a tree with low error. And there are lots of possible trees, n to the 2 to the d of them, but because decision trees have this nice hierarchical structure, there's an efficient, n to the d time, recursive algorithm to find the one that minimizes error. And it really just works like this. You try every possible route, you recurse on both subtrees. If d equals 0, you're just returning the leaf learner. You're running the leaf learner to get the leaf hypothesis. And then out of all the trees you built, one for each possible route, so there are n of them, you return the one that minimizes error on the test set. So this is just a recursive backtracking algorithm with branching factor n, so it runs in n to the d time. The extension to subcube partitions, I don't have time to go into much detail, but this is different. It's not recursive. It's actually a greedy algorithm. It's inspired by greedy set cover. And the resulting hypothesis is not exactly a subcube partition. It's something different, but the parameters are basically the same. Sample complexity is like m times s, where s is the size of the partition. Time complexity is t times n to the d. So just to wrap it up with the big picture, the point of this work is to try to interpolate between distribution-specific pack and distribution-free pack, and we're doing this via decision tree and subcube partition complexity. There are, more research directions in this area where we just want to explore different types of distributional complexity and get learning algorithms that scale with each of them. So it's, good to think about what other distributional complexity measures we might want to consider and how we might be able to take advantage of simple distributions to give more efficient learners. And that's it.
Thanks for the great talk. We have a sufficient amount of time for questions, if anyone has some.
Thanks for a great talk. can you also handle rank of the decision trees instead of the depth?
Ooh. Let's see. So I know a decision tree search algorithm that runs in like n to the r time, where r is the rank. I don't think it directly minimizes empirical error though. So I'm not sure if that algorithm would work right out of the box, but perhaps, I guess.
Are there any other questions? I guess it would have been nice if I was in the corner, but thanks so much.
Thank you. So could you go back to the main results slides?
Yeah.
Right. So for in the extreme where we have a distribution specific setting, do you think, so is it obvious that the sample complexity is optimal? So can you avoid exponential dependency in D because you have a very specific simple structure on the distribution?
I'm not quite sure what you mean by that. So, but like distribution specific in this setting, do you mean something like the distribution has depth 1?
Yeah,
or
like the ground truth has a finite depth decision tree, for example.
I am not sure I understand. Like if it's depth 1, then you end up with sample complexity m. I'm not sure.
Okay. So here D is the depth, not the
D is the
dimension.
depth.
Okay.
Yeah. There might have been some confusion. D is not the dimension. N is the
Okay.
dimension. D is the depth. Yeah.
Okay.
Sorry.
Okay. Thank you. Yeah.
Any other quick questions? Like extremely quick. Okay. Let's thank the speaker again. Emmanuel? Oh, yeah, we can do it in the normal order. All right. Emmanuel, you're here, right? Yes. Okay, awesome. Maybe we'll use a couple seconds to sit down. There are some chairs here if people want to be comfortable, but you're also allowed to stand, I think. There are a few chairs here as well, and a couple around me. Sorry about that. Start promptly, one sec. Okay, does everyone feel appropriately settled in? Okay, so we'll have a second talk. We'll talk about recovering labels from crowdsourced data, and Emmanuel will give the talk. Let's thank the speaker and let's start.
Thank you. So for the context, I've been doing much of this work right here in UNSLeon.
Can you use the mic?
Oh, sorry. So yes, for the context, I've been doing much of this work here in ENS-Lyon before I moved to Rennes. And this work is built upon earlier work I did during my PhD in crowdsourcing. So let's start with a scenario. Picture a group of workers who are each assigned binary tasks, and so they each need to make yes or no decisions. So there are many situations in practice where it happens. So you can think of image classification, text moderation, or even sentiment analysis. And when you think of crowdsourcing problems, three natural questions emerge. So how do we recover the labels? Can we compare the workers to identify who performs better or worse? And can we estimate the abilities of the workers on a given task? Okay. I'll touch on all these three problems in my talk, but I will be mainly focusing on the central question of recovering the labels. Okay? So let's start with Niels. Okay, no. So I'll break this down into three parts. So I'll first introduce the isotonic model, then present two existing methods, and finally go over the approach I've developed in my work and try to give some insights. So let's start with this illustration. So each task consists in giving a label in -1 or +1. So there is a vector of -1 and +1, and we observe the responses of the workers. So, for example, +1 or -1 responses. So each column represents a worker, and each row, represents a worker, and each column a task. So we can have partial observations. So you just put 0 coefficients in those matrix positions when you have missing values. And lambda here represents the rate of partial observations. So lambda is 1 when you observe all the coefficients of the matrix. Okay. So how do we model this? So I assume that we observe a matrix Y, which follows this relation. So here, X star is the vector of unknown labels. E here is a matrix of independent sub-Gaussian noise. And M is the unknown ability matrix of the workers. So when MIK is equal to 1, it means that worker I is very good at task K. And when MIK is equal to 0, it means that worker I is very bad at task K. Okay? And B, you can see B here as a Bernoulli mask, so which allows us to model Bernoulli partial observations. Okay. So up to now, I have only assumed that M has coefficients in 0, 1. Now I'll put some shape constraints on M, which represents the ability matrix of the workers. So we assume that M is isotonic up to a permutation of the workers. Okay, so it means that it has increasing columns up to a permutation of its rows. Okay. So on average, if you take 2 workers, one is either uniformly better than the other or uniformly worse, on average. Okay, so to recover the label, natural loss is the Hamming loss. Okay, maybe everyone. Okay, so it simply consists in summing all the mistakes you've made. But I won't consider Hamming loss here. I'm considering square norm loss. So you just restrict the ability matrix M to incorrectly labeled task, and you take the square Frobenius norm. Okay. If workers are bad, so if M is close to 0, the square norm loss is small, but Hamming loss can be very large because it can be of order D if workers are very bad. So a good feature of the square norm loss is that it evaluates the quality of the estimator hat X rather than the performances of the workers. Okay? So that's why I consider mostly square norm loss here. Okay, so if you remember these 3 objectives I mentioned earlier, so there was recovering labels, ranking workers, and estimating their abilities. And so a good thing about this isotonic model is that, okay, you can define this square norm loss, but you can also, in fact, define square norm loss for ranking and square norm loss for estimating abilities. But I won't get into much more details in this talk, okay? And you put just an expectation for the risk. And this brings me to show you the definition of the minimax risk. So you simply take the best estimator hat X in the worst case, and this gives you the minimax risk, okay? Okay, so the main result in my work is that there is actually no computational statistical gap up to a polylog factor, okay? There exist polynomial time algorithms which achieves the minimax rate up to a polylog. And in fact, this minimax risk is of order d over lambda. Okay, so it is non-trivial because it is smaller than n times d, because a trivial bound is n times d. I'll now move to 2 existing methods. So majority voting consists simply in summing all the rows of all columns of the matrix of responses. You just sum everything. And unfortunately, majority voting achieves only the bound of d square root n over lambda. So in comparison to to the minimax risks, you have this square root n here. So you don't have d over lambda. It's not minimax optimal. Then, so in the literature, Shah and co-author introduced the Obi-Wan method. So the main idea is that when you take M diag x star transpose, it does not depend on the unknown labels x star. And you can exploit this fact by using a spectral method. So you compute the left leading eigenvector of y, v hat, and okay, the authors do partial ranking and to estimate the labels after that. But okay, so what's important is using the spectral method. And the authors show that when the matrix M is of rank 1, their methods achieve the minimax risk up to a polylog of order d over lambda. But it only works in the simple model where M is of rank 1. It doesn't work in more complicated, in non-parametric models, such as the isotonic model I've just introduced. Okay, in the isotonic model, you still have this square root n, and this is not minimax optimal. It is comparable to majority voting in the worst case. Okay, so to achieve this d over lambda rate, let me now introduce the iterative spectral voting approach. The core of the approach consists in iterating 2 steps, PCA steps and weighted voting step. For the PCA step, you can just simply, you can do a similar thing as Shah and co-author did. So you compute the left leading eigenvector. And so you do that because the main idea is that since M is isotonic, it is in fact very close to low rank matrix. Okay, so and then so once you have done this, once you have computed this leading eigenvector, you use it to build a vector to do weighted voting. Okay, so you just estimate labels with a weighted vote after that, so I won't get into much more details here. And the idea is to iterate these 2 steps, so spectral step plus weighted voting, to estimate the labels on using the columns of y for which the labels remain uncertain. Okay, so you iterate voting PCA steps plus voting step until you get a final estimator. Okay, so once you have recovered the labels with this approach, or some of the labels, you can use these labels to actually rank the workers and estimate their abilities. So you restrict to a column case such that you have a good guess of the labels, and you use a method from previous work in the literature to estimate pi star and M. And so this gives you a good estimation of pi star n. It can actually be proven to be minimax optimal in polynomial time also. Okay, so let me conclude in 3 points. So there are 3 interconnected problems in crowdsourcing. So recovering the labels, ranking, and estimating abilities. The non-parametric isotonic model is very flexible, and because it can be used to address all these 3 problems. And finally, there is no computational, and most importantly, there is no computational statistical gap in recovering the labels and ranking or estimating abilities. Thank you.
Maybe we have time to quickly crowdsource one question.
I'm not sure I fully understood if you showed that there is no computational statistical gap in general or just for your approach.
In fact, okay, so this approach shows an upper bound.
Okay.
So I give the upper bound, and the lower bound is already known. So the lower bound is of order d over lambda. So my approach shows that there is no computational statistical gap since it can be computed in polynomial time.
Okay, okay, thank you.
Yeah, thanks so much. Let's thank the speaker again. Next, we have Alexander from India giving us a talk about an uncertainty principle for neural networks.
So hi everyone, thanks for being here. So today I'm going to talk about how I work with Antonio here and Francis on an uncertainty principle for linear recurrent neural networks. So very briefly, to be sure that we all share the same values. So linear RNN, basically they are classical RNNs, but very surprisingly, the propagation of the hidden state is linear. And it implies A and B that can be either input control or non-input control transition matrices. And in classical case, A is diagonal. In this case, we use non-input dependent matrices because, as you will see, the task we consider does not depend on the input. And we consider the 1D case, so scalar input and scalar output. So linear recurrent neural networks are pretty convenient in the sense that the recurrence can be unrolled and then computed through a convolution that defines a convolution kernel, a sequence CT, which involves the parameters of the model, so a complex vector A and a complex vector B of size S, which is the dimension of the model. And yeah, so now that you know how linear RNN work, a bit of context and motivation. So as you know, back in the days of LSTMs and unitary RNN, so a bit more than 10 years ago, this kind of architecture were the most used model when it came to modeling long-range sequences and memorizing long inputs. But they've been progressively replaced by transformers, mostly because of the well-known problem of vanishing gradient. But in 2021, Albert Gu and co-authors introduced S4, which was one of the first model linear recurrent neural network that, thanks to a proper initialization of the recurrent matrix and the use of a diagonal matrix, was able to achieve very good results on long-run interaction and long-range benchmarks. So it fostered a lot of research, and today some promising foundation models such as Mamba incorporates linear recurrent unit into their architectures. But the picture could not be that perfect because some papers show that actually this kind of model may have some limitations, and especially so the one on the top from Jelassi and co-authors that we focused on in this paper, and that basically show that perfectly retrieving, and by perfectly I mean like zero error, perfectly retrieving input for the past from the past requires the width of the linear recurrent model to increase linearly with the sequence length, which is a bit annoying when one wants to memorize very long sequences. So based on this observation, we wanted to analyze the potential performances of linear recurrent model. And so we focused on arguably the simplest task that one can think when it comes to modeling long-range sequences and memorizing long sequences, which is the copy task. So what is the copy task? Basically, it's asking the model to memorize input that it saw k timestamps before the processing current stamp. So mathematically speaking, this means that we want our convolutional filter defined in the introduction to approximate the ideal filter, which is what we call the shift k filter. It's basically the Dirac shifted of k time step in the past. And so to model that, we consider any real valued infinite length stationary signal whose autocorrelation function is pretty classical. It's just exponentially decaying. And so this task is pretty convenient in the sense that the law of large numbers and the stationarity of the signal allows to define the loss, a loss that only depends on the autocorrelation function of the signal and the cross product of the two filters that we consider. So that was for the task that we consider, and we wanted to fully analyze the performances of linear models for this task. And so to do so, we started with trying to derive lower bound to provide a benchmark for evaluating the performances of linear models and more generally linear time invariant filters for the copy task. And so we did it both in the white noise and the autocorrelated case. So this is the result. So the lower bound in the white noise case, so no autocorrelation. So you see that the lower bound, basically what the conclusion you can draw from this lower bound is that linear RNN suck at memorizing white noise, because in the case of interest here, so large K, the ratio S over K is very small, and so the loss is basically 1, and a linear model cannot memorize long-range interaction, long-range sequences of white noise. But this gives a first hint into the following of the paper, which is the inherent trade-off between the width of the model, so S, and the horizon of the task, which is K. And for the proof, I don't have time to dig into the details, but basically it's just optimizing a quadratic form with respect to the parameter B, and then it gives a performance criterion, which is pretty tedious, but manipulation of discrete Cauchy matrices and rational approximation on the unit circle allow to derive the result. So that was the lower bound for the white noise case, and to give a finer picture and to get closer to real case scenario with autocorrelation, we added autocorrelation in the loss. And so in this case, you have this lower bound, where the plus is the max between 0 and this value. So we still have this dependency on the ratio S over K, so still a trade-off between the width of the model and the horizon of the task. But the most important thing here is the dependency of the lower bound on the autocorrelation of the data. And so you can see that the higher the autocorrelation, the lower bound. So this means that this could mean actually that the performances of the model is highly depending on the spectral characteristic of the data, which is pretty interesting, and it's a behavior we wanted to understand later. And for the proof, it's pretty similar, just the incorporation of autocorrelation allows to add a new pole, so new value for our complex vector A, sorry. And the following is pretty similar to the white noise case. So that was for the lower bounds, both in the white noise and the autocorrelation case. And the conclusion we can draw from this is that there seems to be a trade-off between the width of the model and the horizon of the task, and also the performances of the model highly depends on the autocorrelation of the data. And to understand it a bit further, we wanted to provide a closed form parametrization of the model that achieves very good results close to the lower bound, and that explains this behavior. And so to do so, we introduce a new parametrization of the model. So we were motivated by the frequency representation of the loss. So basically it's taking the discrete Fourier transform of the time domain loss I showed you before. And so this involves the transfer function of our convolution filter, so capital C, which is just this sum of individual terms, and the transfer function of the ideal Dirac filter, which is just the high frequency complex exponential. And so you can see that a good filter that minimizes this loss should be able to approximate the complex exponential pretty well on the unit circle. So this motivated us to propose this parametrization for the poles, so for the neurons of our model, because basically we wanted every individual term of the sum which defines the transfer function to approximate one oscillation of the exponential. And so this motivates to put all the weight on every oscillation of the complex exponential, and this gives this proposal for the poles, which is pretty surprising, because actually all the poles have a constant modulus and their phases are uniformly spread over a slice of the unit disk, a slice of size pi s over k. And what is funny in this is that there is a strong link, strong link with the hypo initialization, which is the initialization of the S4 model that I mentioned in the introduction. So we motivate this very performing and very good initialization by a complete different explanation, which is that the models want to memorize far in the past. So this was for the proposal for the poles, A's, and optimizing the loss with respect to fixing these parameters, provided the expression for the last parameters, which is the vector b. And so we have a vector b, which is proportional to -1 at the power s, s being the index. And so this gives a full closed form formula for our new parameterization. So we have defined a new filter, and what is reassuring is that this filter actually performs pretty well on the copy task. By pretty well, I mean that we achieve a loss that is similar to the lower bound up to a constant factor. So this is reassuring. This is true in the asymptotical case, but this is the case of interest here because we consider long-range sequences. And so we have this pretty good loss. And so this shows that the conclusion we can draw from the behavior of this model may explain the optimal behavior or linear model on the copy task. And what is this behavior? So in the frequency space, you have in blue the complex exponential, and in green you have the model that we approximate, our model, and you see that we approximate very well the complex exponential on a narrow window in the frequency space. And so this explains why linear models are bad at memorizing white noise, because white noise has a very broad spectrum, and so shrinking the window in the spectral domain, so adding autocorrelation, increase the performance. This is why we have this. And in the time domain, this is what we call the uncertainty principle, which basically means that actually our parameterization shows that it's not complicated for linear models to memorize far in the past, but increasing how far we want to go comes at the expense of resolution. So this is this inherent trade-off between the width of the model and the horizon of the task. Thank you.
I think we can still do one question if someone has a quick question. If no one does, I actually had one. So one question, so because all of your stuff seems fairly general, do you have a sense for what tasks are easy and what tasks are hard for these linear models? Like the shift was one thing that I guess people have observed in practice, but do you think there are other tasks which like also are hard and like maybe we should think about other things for?
Actually, some results show that this kind of model are theoretically universal, but the problem is when it comes to modeling long range. And so for natural language, these models are pretty good, but the problem is really when it comes to long range. And so this, and a lot of papers around, shows that there's no limitation actually in the sense of the complexity of the task. It just has like there is a, you have to choose between the resolution you want and the width, the complexity you can have in your model.
Thanks, I think I understand. Any quick questions? Otherwise, we can move to the last speaker. Okay, let's thank the speaker again. Yeah, we'll have the last speaker of the session talking about learning intersections of two margin half spaces, and Ming Chen will be giving the talk.
Okay, thanks. In this work, we study learning intersection of half spaces. Joint work with Elias, Li Sheng, and Christos. An intersection of half spaces is defined by k half spaces, and positive is labeled positive. An example is labeled positive if and only if it is labeled positive by all the k half spaces. And given some sample size to a distribution consistent with an intersection of half spaces, we want to output some hypothesis with small classification error with high probability. And it's known from VC theory that if we can implement the consistent hypothesis finder, then for any realizable distribution, this problem can be solved with roughly dk over epsilon sample complexity. However, it has been shown that implementing such an algorithm is NP hard, which gives a hardness of distribution-free proper learning of this problem, even for learning two half spaces. Surprisingly, so very little is known about the computational complexity of this problem. Although there are some complexity about the representation hardness of this problem, or some hardness of learning super constant many of half spaces, It is even unclear whether in the distribution-free setting we can learn an intersection of two subspaces in polynomial time. So to bypass the difficulty of distribution-free learning, there are many works try to solve this problem by making some additional assumptions over the marginal distribution. For example, if your marginal distribution is Gaussian or uniform over hypercube, then for fixed parameters, you can develop algorithm runs in poly-D time. But the issue is that in this line of work, the distributional assumptions are usually very strong, and the algorithms works in this setting are very hard to be generalized because useful structure results of the underlying problem are not getting used or even discovered. So to make him more practical distribution assumptions, but still making the problem more tractable, another popular option is to assume that the underlying hypothesis has some margin. Roughly speaking, margin assumption assumes that every example is at least a gamma far from your target. And this margin assumption is widely known for the succeeding of learning a single subspace because of the perceptual algorithm. However, things change if you want to learn an intersection of two margin subspaces. And the best algorithm for this setting has a quasi-polynomial running time with respect to the margin, which was developed by Clevens and Savidio in roughly 20 years ago. And as an open question suggested by Clevens and Savidio, it's unclear whether margin is a fundamental bottleneck of this problem. And it's unclear whether there is a poly-D or gamma time algorithm that can learn an intersection of two margin subspaces. So in this paper, we studied an intermediate setting between the well-studied distribution-specific setting and the less understood margin setting. Specifically, besides the margin assumption, we also assume that the marginal distribution can be written as a product distribution as dv and dw, where v is the subspace spanned by the two defining vectors, and w is its orthogonal complemented. Importantly, we make no further assumptions over either dv or dw. So the problem of learning functions under factorizable distribution can date back to the problem of learning k-subspace hutas professed by Van Pala and Xiao. In fact, many where the target function only depends on the projection of examples onto some low-dimensional subspace. And in fact, many well-studied tractable setting is just a special case of this learning under factorizable distribution. However, as we mentioned previously, the previous tractable setting always make very strong distribution assumptions and fails to discover new and useful structure results. This quasi-polynomial time complexity is still the best known time complexity for this algorithm, for this problem. So if we have an efficient algorithm that can learn this intersection of half spaces and a factorizable distribution, this would significantly generalize the previous tractable settings, such as learning under Gaussian. So let's do some algorithm review. So like most PAC learning problem, the central, the core ingredient of this problem is to find a correlation statistical query or a weak hypothesis that has some small correlation with respect to the target. Because if you can do this for any marginal distribution, then running a standard boosting algorithm, you will get some hypothesis with epsilon small error. And at the heart of the previous best known algorithm, under margin assumption, an intersection of two subspaces can be represented as a PTF with degree log 1 over gamma with some small margin. This implies that you can actually find in time d to the log 1 over gamma CSQ that has some weak correlation with respect to the target. So if there is a faster CSQ algorithm that can find a query with larger correlation, we get some improvement over the previous best algorithm. But unfortunately, as our first theorem indicates that, any pure CSQ algorithm, even under factorizable distribution, that want to weakly solve this problem, must have a running time roughly d to the log 1 over gamma. And this means that this polynomial representation method developed by Clevens and Savidio is qualitatively optimal among all CSQ algorithms, even for factorizable distributions. And if there is some faster algorithm, it must lie out of this CSQ framework. So the intuition behind the CSQ barrier is that any CSQ algorithm is only able to ask a query of the form y time q of x. So for any instance, there is always some region within which you can use very simple query to get polygamma correlation. CSQ algorithms do not have the ability to learn information from the marginal distribution, and almost all the queries made by this algorithm have zero response. And this actually motivated a natural improved algorithm framework. When the underlying instance is indeed CSQ hard, can we design instance-dependent queries with good correlation by first learning some information from the marginal distribution? And the answer is yes. Our mean theorem gives an efficient SQ learning algorithm, such that for any input distribution consistent with an intersection of two margin subspaces, as long as the marginal distribution can be factorized, this algorithm draws polynomial number of examples and running in polynomial time with respect to all the input parameter and output a hypothesis with good with small classification error with a very good probability. This qualitatively improved the previous quasi-polynomial running time and generalized the previous tractable setting, such as learning under Gaussian. And there is also interesting implication is that this theorem shows that CSQ algorithms and SQ algorithms indeed have a super polynomial separation in terms of weakly realizable Park learning, while previously such a separation is known for strong learning. To get the improvement, the core challenging is to understand when the underlying instance is indeed CSQ hard, what information can we learn from the marginal distribution? This requires to discover some new non-parametric structure result of this problem. And our new structure result indicates that even without marginal distribution, if we center the marginal distribution to have zero mean, and if the first three moments of positive or negative example match each other, then the marginal distribution must have a very large third moment along some direction. To prove this, we introduced some novel technique we call the one-sided polynomial approximation. Roughly speaking, if you want to prove that the distribution is restricted at some region that satisfies some moment constraint do not exist, you can construct some very special form of polynomial as a certificate to verify this fact. However, it is still challenging to understand how to use this structure result properly. So to make the way we make use of this structure result is inspired by the independent component analysis framework by Van Pala and Xiao. In their work, they have this key observation. For factorizable distribution and for m greater than or equal to 3, if the marginal distribution has the first m-1 moment the same as the Gaussian but not the mth moment, then you can solve a sequence of non-convex optimization based on the mth moment information to get a list of poly D vectors, such that one of them is in this relevant subspace. Although some very special case of this ICA problem can be solved in polynomial time, due to the numerical stability issue, so far there is no known polynomial time algorithm for this ICA. And in this work, we bypassed the difficulty of fully solving the ICA and gave a polynomial time algorithm, such that for any input distribution, this algorithm runs in polynomial time and with non-trivial probability gave a vector that is a polygamma close to the relevant subspace. As we mentioned earlier, after getting such a direction, even without factorizable distribution, you can efficiently do weak learning. So you can just run some standard boosting algorithm to get a strong learner. And as a conclusion, in this work, we gave a polynomial time algorithm that learn any intersection of half spaces with margin, as long as the marginal distribution can be factorized, which relies on new SQ weak learning framework together with some novel structure result of the problem. And this also implies a super polynomial separation between CSQ algorithms and XQ algorithms. As for future directions, it's natural to consider whether we can efficiently learn intersection of multiple half spaces with margin and factorizable distributions. And more importantly, we still have some distance to understand whether learning intersection of two margin half spaces can be done in polynomial time without these factorizable assumptions. So that's my talk today. I'm happy to take questions.
We have time for a couple of quick questions, if anyone has any.
Hi, thank you. Can you please maybe go back to your factorizability assumption and maybe explain and motivate it a little bit?
this one. So basically, this assumed, in fact, many tractable setting actually assume that you have a Gaussian marginal distribution, and the problem is the label is just defined by some low-dimensional projection of the example, and you want to do some feature learning. And in this case, most of the works assume that the marginal distribution over V or W are standard Gaussian. But here we assume that we place no assumption on either dV or dW. I think in this work, this is just a way that we know how to use our new structure result properly to get some improvement over the previous tractable setting. So it's unclear if we remove this factorizable setting, whether we can still get a fully polynomial time algorithm to learn to margin half space.
So it's just basically you're saying it's a product distribution in which one part is whatever the subspace spanned by the hypothesis.
Yeah.
And you make no assumption on
we
there.
make no assumption on both dV and dW.
I see. It's
dV
just
and
that
dW can be arbitrary distributions.
and it factorizes with in the same
yeah.
direction as your hypothesis. Okay.
Can you handle if there was like a few other spurious directions along the factorization? Like let's say it was in a small dimensional subspace that contained the features, but like a few extra dimensions?
I think this question is not immediately to get answered.
Yeah, thanks so much. Let's thank the speaker again. I think that brings us to the end of the session, and we should thank all the speakers one last time and maybe go to the keynote talk.